it is section 8.8 improper integrals. Up to now, we require the definite integrals to satisfy two properties. Number one, the domain must be finite. And number two, the range of the integrand must be finite. However, in practice, we often encounter problems that fail to meet one or both of these conditions. In either case, the integrals are said to be improper and are calculated as limits. Let's see this first type of improper integrals, and that is along with infinite intervals. Evaluate the integral from 0 to infinity e to the minus x over 2. For this problem, we chop the domain up to b, and after getting this integral, we try to take a limit as b approaches infinity. Pictorially, it's given in this way. Now, we have to get the integral from 0 to infinity. Now, we try to get integral from 0 to b, and we try to push b to infinity. That's how we can get the integral. Okay, once you consider this portion, then now the domain is bounded, finite, and also the integrand is finite, so that we can get the integral as usual by using earlier technique. Okay, here, let's try to finish this computation. Okay, that is the same as now limit, the same limit, and then now for this one, antiderivative is, okay, let's see here, e to the minus x over 2 is the main part. And then if you are making derivative, then minus half will come out. So that, let's see, minus 2 here. So that is antiderivative, and from 0 to b here. So here, that is now limit, same limit, and now twice, and once it's 0, then it's 1. Once it's b, then that is e to the minus b over 2, right? Okay, so we got the here integral for this portion, and we have to take a limit. As b approaches infinity, we know that this value converges to 0, so that the limit must be 1. So that is now the final value. In this way, we try to get the improper integral by using the limit technique. Okay. So here we have the official definition for improper integral of type 1. Type 1 is dealing with infinite intervals. Okay, here, if fx is continuous on 0 to infinity, then the improper integral can be computed in this way. Once the value finite, then we say that that is the value of this improper integral. And also, once f is defined for the up to negative infinity, then here integral is now along with a variable a, and we try to, after getting this integral, we try to take a approaches minus infinity. Once the limit exists again, then now we just get the value for this integral. Okay, now sometimes the integral, improper integral is defined from minus infinity to infinity, then you have to cut the whole domain along with a point C such that you have to get left side and right side integral, and then you have to sum. And this C must be an arbitrary point. So for any point C, the left-hand side, left to infinity interval and right infinity interval, the improper integral, both of them should be finite, and the sum will be the improper integral. Okay. Now, in each case, if the limit exists and is finite, we say that the improper integral converges and that the limit is the value of the improper integral. If the limit fails to exist, then we say the improper integral diverges. Okay, here, determine whether the integral is convergent or divergent. Okay. Now, for this one, because it's infinite interval and the given integral must be written in this way, limit, okay, b approaches infinity, and integral from 1 to b, now 1 over x dx. Okay. For that one, the same limit, and then antiderivative of this one is logarithm of absolute value of x. Now, we have to evaluate it from 1 to b, then that is same as the same limit, and then here that is logarithm of b, and logarithm 1 is 0. Okay, so we have this one. Now, b is approaching infinity, then this value will become infinity. So it is not convergent, it is divergent. Okay. It's the area under the curve y called sine x over x squared from 1 to infinity finite. If so, what is its value? That means that we have to get the integral, improper integral from 1 to infinity and logarithm x over x squared dx. We have to get it. Now, from now on, rather than using b and limit b approaches infinity, we'll try to use infinity notation. Then you can understand the meaning quite easily. Anyway, for this one, now once you try to get the antiderivative, then probably you may try to use here the technique, integration by parts. From this, for this one, you may choose u equal logarithm x and v prime equal 1 over x squared. Then from here, u prime will be 1 over x, and here v must be minus 1 over x. So that for this one, now uv, which is minus 1 over x and logarithm x, and now bottom and top is 1 and infinity. So rather than using b over there, and then limit b approaches infinity, we try to use that notation. But we have to understand this one and as the standard definition. Okay? Okay. Now here, minus, and here u prime v, that is minus 1 over x squared. So the minus will come out, and then here from 1 to infinity, 1 over x squared dx. Okay. For that portion here, once, okay, but for that one, once x is 1, then the value is 0. Once x goes to infinity, then we know that x is growing much faster than logarithm x, so that it is approaching 0. Okay, the value will be 0. Now, for this one, its antiderivative is minus 1 over x, and from 1 to infinity. Now, once it is 1, that is 1, but if it is infinity, then it is approaching 0. So that we can write in this way. That is 1 minus 1 over infinity, right? So it is a 1, okay? Okay, so the whole area is 1. Okay, let's see this problem. For this form of integral, and we'll see in application quite frequently, so that we'll try to figure out when this integral converges. For what value of p does the integral converge? So we'll try to figure out. Okay, number one, when p is 1, then there is 1 over x. Integrand is 1 over x. And then already we know that this is divergent. Earlier we solved that here, but we'll do again here. Now, so that given integral becomes here from 1 to infinity 1 over x dx. Now for that one, there is a logarithm x. It's positive, so that you don't have to put absolute sign from 1 to infinity. Again, the infinity means that here there's a b, and you consider here limit b approaches infinity. Okay. For this one now, logarithm infinity, which is infinity, logarithm 1 is 0, so that becomes infinity. So it is divergent when p is 1. The secondly now, when p is non-zero, not 1, okay, then here, okay, now given integral is integral from 1 to infinity, we may write this one in this way, x minus p power and dx. Its antiderivative is 1 over minus p plus 1, so that 1 over 1 minus p, and then here x to the minus p plus 1, so 1 minus p, right? Now evaluate from 1 to infinity. Okay. Now, if the power, okay, from this one we have two cases. Now, p is now larger than 1. Okay, larger than 1. Then power 1 minus p is less than 0, so that once x equals 1, and then always the value exists. However, now if x approaches infinity, then here p is larger than 1, then 1 minus p, the power is less than 0, so that it converges to 0. So that in the case, the given integral is approaching to here when x is infinity, the value goes to 0, so that here, that is now we have, once it is 1, then that is now 1 over 1 minus p. Okay, here we're with a minus over there. So we can write down here that is 1 over p minus 1. So once p is larger than 1, we have this value. Of course, this is a convergent. Right? And how about p is less than 1? Right? Then, now p is less than 1, then 1 minus p is positive, which means that here, x to the 1 minus p, along with a positive power, x approaches infinity, then this value go to infinity, blow up, so that is divergent. So only when p is larger than 1, it is convergent. Okay, so only the case here p is larger than 1, it is convergent. Yeah, when p is larger than 1, the improper integral converges to 1 over p minus 1. Okay. Determine whether the integral converges or diverges. Evaluate if it converges. Okay. For this one, okay, here, if we try to find the antiderivative, then there is a minus 2 e to the minus 5x. Once you are making derivative, then here, minus 2 minus 5 multiplication will become 10. Okay, so that is antiderivative, and we are evaluating from 1 to infinity. Okay, so that here, along with 2, and along with this negation, we first try to evaluate from this bottom, then there is e to the minus 5, and minus and infinity, so that e to the minus 5 times infinity. Okay, that is converging to 0, so that the value must be twice of e to the minus 5, right? Okay, that's the final answer. We are using here notation infinity here, but infinity is not a number, but you have to understand this one in this way. Okay, rather than here infinity, we may put this one as b and try to put here now limit and b approaches infinity. So I'll use this notation, but you have to understand in this way. Okay. Determine whether the integral converges or diverges. Okay, same kind of problem. Okay, for this one, now you have to find the antiderivative in order to do that. Here looks like by using partial fraction technique we can get it. Okay, so let's try to manipulate the integrand 1 over and x and x plus 3. We have factors for this denominator. That one is now a over x plus b over x plus 3. Then from this one, here the same common bottom x and x plus 3, and ta will be 8 times x plus 3, and here b times x. So that here that is a plus b of x and plus 3a. And then here that same bottom, right? So it must be 1. So that means a plus b must be 0 and 3a must be 1, which means that a is 1/3 and b is minus 1/3. Okay, so here the given integral is changed into this way. Now that is integral, okay, 1/3 may come out, and then 1/3 integral from 0 to infinity, and now 1 over x and minus 1 over x plus 3. Okay, so that is here 1/3, and this one will make okay, not this is 1. This one will make here, that is logarithm of x and minus logarithm of x plus 3. And we are evaluating from 1 to infinity. Now, we reorganize this one and 1/3 of that. And then that is a logarithm and x over x plus 3. Right? And then here from 1 to infinity. Okay, once it is infinity, then this one is approaching 1 so that it'll become 0. So at 1/3, and there's a 0 and minus. Once it is 1, then there is a logarithm and 1/4. Right? Okay. So now the final value must be here, and 1/3 of, okay, along with this negation, we can put over there logarithm 4. Okay, that's the final answer. It's convergent, and the value is here 1/3 of logarithm 4. Okay. Okay, the same kind of problem. And for this one, now we can rewrite this one in this way. That is here minus infinity to 2 and divide by 4 here. Then divide by 4, divide by 4, so that here top will be 1/2 and on bottom will be x squared over 4 plus 1 and dx. Right? Okay, what is antiderivative? Looks like arctangent, right? Arctangent. Okay, let's try to see here some coefficients times arctangent of x over 2, right? Then arctangent, you know. So its derivative will make here 1/1 plus that term squared. That's exactly this one, and its derivative 1/2. So exactly that one. So here we may ignore this portion. That's 1. Okay, and here we put minus infinity to 2. Okay. Now, once it is 2, then that is now arctangent of 1, which must be here pi over 4, and minus here arctangent minus infinity. So the arctangent of basically this whole thing will be minus infinity. Right? That is pi over, in fact, this whole thing is minus pi over 2. Okay, so that is now pi over 4 and minus pi over 2, right? So that is here 4 and 3 pi. Okay, that's the final answer. It is convergent. Okay. Okay, again, same problem. Now we have unbounded domain and from minus infinity to infinity. So for this problem, and you have to get two integrals. For example, from minus infinity to here 0, and second one is from 0 to infinity. So along with that two portion, we have to get integration, that is 2x over now x squared plus 1, that squared, right? That is dx. Okay, so we say this is part 1, the first one is part 1, and second one is part 2. Then part by part, you have to get the value, okay, plus and part 2, okay. Okay, for part 1, okay, that's same as from minus infinity to 0, and that is top is 2x and bottom is now here x squared plus 1 squared dx. Its antiderivative looks here minus 1 over x squared plus 1. Then if you are making derivative, then okay, for this one power is minus 1, so minus 1 will be cancelled and minus 2, and its derivative is 2x, so that is antiderivative. Okay, now for that one we are evaluating 0 and minus infinity. Okay, for this one here, okay, if this goes to infinity, then this whole thing will go to 0, so that when it's 0, the value is minus 1, and the second portion will be basically 0, so that the value is minus 1 for part 1. Now, secondly, here for part 2, we have to get the value from, that is from 0 to infinity, and same integrand. Of course, here now the same antiderivative, and that is from 0 to infinity. Okay, when x is infinity, the value over there is 0, and here now when it's 0, then it's minus 1, so then minus 1, which is now 1. So both sides, the value exists, and then the summation is 0, so that the final answer is 0. It is convergent, and the final answer is 0. Okay? Okay, that's the first part of the section, and we'll continue in the second part. Thank you.